Alright, so this video is going to be part 7 of our sequences and series review. This is going to be the third video out of 3 on our series tests. So just trying to see if a series is going to converge or diverge, and we have our last 2 tests to go over, the ratio test and the root test. First, I want to go over though absolute convergence and conditional convergence, what we're talking about there, why they're useful. And well, absolute convergence, right, we know that that's when the series with the absolute value of a sub n is convergent. Okay, and we know that if something is absolutely convergent, well, then it is convergent as well. Okay, so if the absolute value of a sub n is convergent, well, then just regular a sub n will be convergent as well. All right, that's something that you should know. Now, what about conditional convergence? Well, this is when your a sub n is convergent, but your series with the absolute value of a sub n is divergent. Okay, so I'll give you some examples of both here. For absolute convergence, if we have something that we know converges, like the sum from n equals 1 to infinity of 1 over n squared, we know that that's a p series, p is greater than 1, and that converges. If we put absolute value there, it's not going to change anything. Okay, it's still going to be convergent. So that is an example of absolute convergence. Okay, it doesn't matter if you take the absolute value or not, it's still going to be convergent. Now, what about conditional convergence? What's a good example there? Well, say we have the sum from n equals 1 to infinity of the, let's do the alternating harmonic series. Okay, we have -1 to the nth power over n. Now, as it stands right now, this is convergent by the alternating series test. Okay, we've done that before. Now, if you take absolute value, what you get is the sum from n equals 1 to infinity of 1 over n. That's the harmonic series, and that's divergent. So this is an example of conditional convergence. Now, when is this stuff useful? Why do we care about this at all? Okay, well, take for example something like the sum from n equals 1 to infinity of cosine of n over n squared. Okay, this cosine n. Okay, it's not going to have it's not going to give you a numerator with alternating signs, negative and positive, and it's definitely not going to be all positive or all negative or anything like that. Okay, what this cosine of n is going to do is it's going to have maybe a couple positive, maybe like 2 positive, 3 negative, 3 positive, 2 negative, something like that. It's not going to be a nice pattern at all. Okay, it's not going to be alternating. So what we do to prove that this is convergent is first prove that it is absolutely convergent. And I did a great example of that in the explanation video for absolute and conditional convergence if you're interested. Okay. Now, before we get into the ratio test, I really want to make sure that you guys understand absolute convergence and conditional convergence, okay? So definitely make sure that you really have that down pat, because you're going to be asked questions to see, okay, is this absolutely convergent, conditionally convergent, or divergent? And that probably will be the majority of the questions that you'll be asked on something like a Calc 2 final or even your sequences and series test. Okay, it's not just going to be, is this convergent or divergent? It will be, is this absolutely convergent, conditionally convergent, or divergent? Okay, that's generally what the question that you will be asked will be. So, on to the ratio test. Now, the nice thing about the ratio and root test is that they prove absolute convergence. Okay, so yeah, that kind of answers the question already for you. Okay. Now, what we have to do is take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, right? If it's less than 1, then you get that your series is absolutely convergent. If it is greater than 1, then you get that your series is divergent, and if it equals 1, then it gets that you get that your test is inconclusive. Now, so some more things to really say on this before we do a quick example. If you see a factorial in your series, like for the example that we're about to do here, I might as well just write it down. For the example here, what did I have? We have the sum from n equals 1 to infinity of 4 to the n over n factorial. if you see a factorial in your series, okay, and I have a checklist of all the tests to go through and everything like that, but if you see a factorial, jump straight to ratio test, okay? That is really the only test that can really handle factorials, okay? Anyways, other than that, the ratio test, if you end up getting that the ratio test is inconclusive, there was probably a better solution earlier on in that checklist that I gave you. I don't know if some of you may not be familiar with that. The checklist, and I'll go over this in another video, that I gave you is called DICLAR. All right, it's an acronym for all of the 7 tests for proving if a series is convergent or divergent. You have the divergence test, integral test, comparison, limit comparison, alternating series, ratio, and root. Now, if you're at this step already, you're at the ratio test, and you get that it's inconclusive, there was probably a better solution before the ratio test. Okay, there's probably something better. So what I would do is go back to something like that. Now, that's something that I've definitely had to do on a test before. Okay, the best thing for me always was to go back. So definitely take my word for that. Okay, and every time that happened, I found a better solution in one of those series or one of those tests before. All right, so now for this example, let's get on with this. Let's take the limit as n approaches infinity of a sub n plus 1 over a sub n. Now what a sub n plus 1 is saying is we're going to put in a n plus 1 everywhere we see an n. Let's do that. We get a 4 to the n plus 1 over n plus 1 factorial, and that's going to be over a 4 to the n over n factorial. Now what I like to do when we do ratio test problems is I like to group kind of the I guess you could say kind of like the like terms almost, okay? This 4 to the n plus 1, I'm grouping that with 4 to the n, and you can see me do that here. I take the limit as n approaches infinity of the absolute value of, now I'm going to do this 4 to the n plus 1 over 4 to the n. I'm going to put those together, okay, because they're going to be really easy, and you can kind of see that you'll get some cancellations here when you divide out those two values. Now, next we have a n factorial over n plus 1 factorial. So now I'm going to put the factorials together here. Okay, and now this just becomes a pretty easy limit to solve. Okay, you have the limit as n approaches infinity of, well, this becomes just a 4, right? When you divide this, you have to subtract the exponents, and you're just subtracting an n here. If you subtract an n from n plus 1, you get just 1, okay? So that's 4 to the first power, and so I'm going to draw this down here. That's not a good arrow. Nope, still not good. Okay, the limit as n approaches infinity of the absolute value of 4, and that's going to be over, well, what comes out of this n factorial and over n plus 1 factorial. Now, n plus 1 factorial, that is the same thing as saying n plus 1 times n factorial. Okay? Because all n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, right? And n factorial is n times n minus 1 times n minus 2, okay? And so on and so forth. So really the only addition for an n plus 1 factorial is that n plus 1. That's the only thing that you're doing differently with an n plus 1 factorial versus an n factorial. So we're able to split it up like this, and that means we're just going to cancel those n factorials and have an n plus 1 on the bottom for our limit here. Now, as n approaches infinity, we're going to get an infinitely large denominator, and that means that this limit is going to equal 0, and 0 is less than 1. So we know that this series is absolutely convergent by the ratio test. Now lastly, we have the root test, okay? Now the root test, well, it's basically the same thing as the ratio test. It has the same, if it's less than 1, it's absolutely convergent. It's greater than 1, divergent. If it's equal to 1, it's inconclusive. But the only thing that's different is what's inside the limit. Okay, now what's inside the limit is the nth root of the of absolute value of a sub n. That's what's different, okay? So if you can remember that, you're good. That's pretty much it. And you know the ratio test, well, you're fine. And as far as when to use the root test, it's very obvious when to use the root test, okay? And this isn't really another one where you know, if you see a factorial, go straight to ratio test. If you see everything is to the nth power, like in our example here, I wouldn't necessarily jump straight to the root test, because you might have something easier in the divergence test, okay? Now, if you jump straight to root test every time, what might happen is that you end up with the limit equaling 1, meaning that the test is inconclusive, and then you wasted all that effort when maybe you could have just proved that it was divergent by the test for divergence, okay? That if you get that the limit is equal to 1, and the, you know, makes the test inconclusive, I would definitely, my bet would be that it was just a test for divergence problem, okay? So anyways, let's do our example here, the sum from n equals 1 to infinity of n to the n over 4n plus 1 all raised to the n. We can rewrite this, okay? Get this n's out of here. We can rewrite this whole thing to the nth power. And then this kind of really starts to make sense why we would take the limit of this exact thing, the nth root, to cancel out this nth power, right? So let's take the limit here. Take the limit as n approaches infinity of the nth root, the absolute value of n over 4n plus 1 to the nth power. Now we don't need those absolute value signs because everything inside is positive anyway, okay? So, and we know that the nth power is going to cancel out with the nth root, right? That's what makes the root test so nice. And we end up with the limit as n approaches infinity of n over 4n plus 1. And of course that limit is, since we're focusing on the highest power of n here, we have a coefficient of 1 on the top for our highest power of n, which is just n, right? And the highest power of n on the bottom is also just n to the first power, okay? So since those match up, all right, we can just look at the coefficients and determine the value of the limit, and that's going to be 1/4. 1/4 is less than 1, so we know that this is absolutely convergent by the root test. So definitely, I mean, the root test, it has the it has the easiest tell. If everything's being raised to the nth power, absolutely go with the root test, okay? But like I said before, I would proceed with caution, because maybe you can try a test for divergence first. That's really the only other thing I can think of. You know, there may be other special cases where it's another test, so you would have to go through the checklist that I mentioned earlier in this video. But generally, I mean, if your test is inconclusive here, I would definitely try to check for a test for divergence or something like that. So that's going to do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for sequences and series and the next video in the series. Lastly, if these videos are really helping you and you would like to consider supporting me, I have my Patreon linked in the description down below, along with some other pretty cool links that you should definitely check out. See you soon.